So the next thing I want to talk about is rotational inertia of a solid cylinder about its central axis, rotating. So in this case, I'm going to draw this picture. So if it's around my central axis, right, it is going to be, this is my axis, and this is going to be rotating, correct? Okay, so solid cylinder about its central axis and it's rotating. Now I can't use linear density and I can't use surface density because it's a solid sphere. But I can use volume density. So in this case, I'm going to use volume density. But in order to do that, I need to divide these into small volume elements. So I'm going to take these to be small volume elements. And this is going to be my dm. And this is going to be my dr. So when you look at a cylinder, what are the things that are required in order to explain that cylinder perfectly? Well, I want to know how high this cylinder is, I want to know how wide this cylinder is, and I want to know how much 2 pi radius I need to go around. So in order to define what a cylinder is, I need to define what its radius is. I need to define what angle that I need to go around it as, and I need to define a variable that I can calculate its height with. Okay? So these are called spherical coordinates. No, sorry, cylindrical coordinates, right? So these are cylindrical coordinates. And that should give you an idea. So this will be a triple integration problem, 1 over r, 1 over phi, 1 over z. Okay? So let's talk about volume density. In this case, the volume density is going to be called rho, because that's just how they define it. And this, instead of being over dm over dA or dm over dl, now is going to be dm over dv. Perfect, right? And the total, rho total, will be equals to m over v. What's the volume of a sphere in general? Well, it is equals to m over pi r squared, or in our case if it's L, and L, which is the length of the cylinder. So if I consider my cylinder to have a length L, and I consider it to have a radius, total radius r, then this little element that I'm talking about in here will have dr, right? This will be dr, this little thing. And then it will have an r little radius that goes from the center to the little sphere that I have chosen. And it's going to have a mass dm, right? The small volume element mass dm. So instead of writing this, I can rewrite this as dm equals rho dv. Now, what is this rho going to be in our, or what is this dv going to be? In cylindrical coordinates, dv, which is the volume element, is given by r dr, d phi, which is the element that goes around, plus dz, corresponding to each of these volume elements, right? Once we have that done, I can plug these values back into my original moment of inertia formula, and I can solve. So for a cylinder, I, for a cylinder, will now be equals to integration r squared. Instead of dm, I'm going to put rho dv, and instead of the v, I'm going to put in r dr d phi dz, right? So this is going to be rho, right? r dr d phi dz. Now, since this is over 3 integrals, instead of 1, I'm going to be able to do 3 integrations. And now let's find the limits of integrations from this. So the first one, we're going to consider it over dr. So first of all, I'm going to rewrite this as rho. Rho is going to be, I'm going to be able to take my rho total out, right? So which is going to be m over v. So this rho, instead of rewriting this as rho, I'm just going to call this m over v because that makes my life easier. And my integration is going to be r cubed dr. My next limit of integration is going to be over d phi. And the last is going to be over dz. Now, what are the limits of these integrations? So where can r go from? The small segment r's that can go from, the maximum can go from 0 to capital R, because that's what I defined my radius to be. So my limits of integration for r are going to be from 0 to capital R, because it can't be any more and it can't be any less. What about phi? Well, my limits of integrations for phi because this is a complete circle, can only be from 0 to 2 pi, because it has to come back to the same point as it started. And my limits of integration for dz, since I called it L, I'm going to call it 0 to L. Take a second and appreciate how easy it was to convert these from limits of integrations, as long as you understand something about what a cylinder will do. Okay? So this implies this is going to be m over v, r4 over 4. So what I've done is I've taken the integration, which gives me r4 over 4, and I've even put in the values. Okay, so I'm not going to do the 2 steps anymore, and I want you to be able to fill these in. Same thing with here, it is going to be 2 pi, and same thing here, it's going to be L. So once I have all of that, I can plug in the v from here. So I'm going to just simply plug these in from here. It's going to be pi r squared L, right? So I took this and I plugged it into here. L goes away, pi goes away, r squared goes away, and what am I left with? 1 and 2, and equals to 1/2 mr squared. So a moment of inertia of a solid cylinder about its center is given by 1/2 mr squared.